So my ultimate goal is to view general relativity from some broader point of view. It is the most beautiful and physical theory, and it describes the structure of space-time in our tiny region of the universe perfectly. However, when we try to extend its validity by 20 orders of magnitude up to the entire universe, it doesn't work. And then we invent new words like dark energy or dark matter. And I believe that the fact is that we should reinterpret the relativity, general relativity, and this is what I am trying to do. However, please relax. I will start with examples for children. Namely, I will try to show how the humanity came to conclusion that the nature tries to minimize something. So my subtitle is how to use them, how not to use them, and what does it mean for the theory of gravity. So the first least something principle was the Snell law. The story begins with a simple mathematical example which we often give to first-year students, namely, the horseman must ride from the point A to B over grass and sand, and he knows that the velocity over grass is higher, so how to find the quickest road? And of course, this is a simple exercise in extremizing, in finding extremum of the real function of a single variable. This variable is just a coordinate of transition point, and it is trivial to show that the minimal value is obtained if and only if this proportion is fulfilled, which is now called the Snell law. And of course, the great achievement of Snell was not to solve this simple mathematical example, but the fact that he had a correct intuition that the same law may apply for the refraction of light. If we replace grass and sand by air and water and the horseman by the light ray, then he had an intuition that the refraction is due to the fact that the velocity in the light velocity in air is higher than the velocity in water, and he concluded that probably the light ray tries to come from point A to B as quickly as possible. Then this may be easily generalized to the Fermat law, describing light rays in an inhomogeneous material. Namely, if we approximate position-depending light velocity by discrete changes, and we approximate the smooth trajectory of light ray by the polygon line, then we know that at each transition point the Snell law is fulfilled, and therefore the minimization of a function of a single variable is now replaced by the problem of minimizing the function of many variables. And now, if we pass to the limit with this transition, we finally obtain the Fermat principle, saying that the continuous trajectory again is such that the time assumes its minimal value, which means that again the conclusion is that the nature tries to arrive as quickly as possible. Okay, then an important variational principle, and actually this was the very origin of calculus of variations, was the brachistochrone problem, formulated by Johann Bernoulli. We physicists, we know at least 4 of those Bernoullis. We know many Bernoulli's law. This one was rather a mathematician. So he formulated his problem as a challenge which he sent to the best contemporary mathematicians, and probably Newton was the winner of this competition, but all of them have solved this problem. The problem consists in to find a curve on which a massive point without initial speed must slide without friction in a uniform gravitational field in such manner that the travel time is minimal among all the curves joining. So this is the brachistochrone problem. So the solution is always, the optimal choice is always a balance between the two tendencies. Short, namely short path, the shorter path is this one, versus fast, the path where the particle or the body assumes high velocity as quickly as possible is this one. And you see that finally, who is the winner? The red one, which is the brachistochrone, and this is again a nice first year or second year exercise for students. Then variational problem for multi-integrals is, for example, the problem of the configuration of an elastic 2D material. So the sheet configuration is described by a single function, namely the z coordinate, depending upon 2 independent variables, and we strongly believe that the actual position of the sheet minimizes the total energy, which is the sum of gravitational energy and the elastic energy. Gravitational energy is proportional to the haze, of course, whereas the elastic energy is proportional to the surface. And the optimal configuration is again a balance between the two tendencies. One tendency to minimize gravitational energy would mean that the sheet goes as low as possible, and here it would have the surface as small as possible. So there is always a balance. And finally, I will finish with my historical remarks with the least action principle, which we usually use in physics. The first version was formulated by Maupertuis, and almost 100 years later, Hamilton formulated the contemporary version of which we now called the Hamilton principle. Maupertuis' motivation was purely philosophical. he wanted to justify the optimistic philosophy of Leibniz, so much ridiculed by Voltaire. If you have read Voltaire's Candide, then you remember that he tries to ridiculize this statement that nature acts as simply as possible, or our world is the best possible. Leibniz tried to answer the old philosophical question: if the good God has created the universe, why there is so much evil inside? And the answer is simple: because God has simply solved the variational problem. The total amount of evil is as small as possible. And if you want to improve something locally, you will then in other places there will be much more evil. So better don't touch it. The God was clever. Okay. So let me finally pass to the mathematical part of my talk, which will be the longest and the most fundamental part. So the calculus of variation. So first of all, we have a space of independent variables, and we have dependent variables. Of course, everything may be nicely organized into a fiber bundle, and those functions are simply sections of some fiber bundle, and so on and so on. Notation. Whenever I add an extra space, very often it is an error, but very often I will probably say, instead of space of independent variables, I will say space-time. Okay, because my main interest is in field theories in space-time. However, a priori it could be just any manifold with any dimension. So whenever I add an extra index downstairs, it means that I consider a partial derivative. When I was young, a student at Warsaw University, I had a feeling that using partial derivatives is a little bit shameful, that partial derivatives are used only by non-educated people from small villages, whereas we educated people, we only use covariant derivatives. Later on, I understood that, of course, it is not true, because, and this conviction was due to the fact that the teaching differential geometry began always with tensors. Tensor was something exceptional, and practically teaching tensors covered 90% of the courses in differential geometry. Later on, when I understood that that most of important geometric structures are not tensors, but for instance are jets of sections, or today I will talk about connections and so on, then, okay, so I will use partial derivatives, and all the formulae, although written in terms of coordinates, are coordinate invariant. Okay? Moreover, in classical courses in variational principles, we always consider one-parameter families of field configurations, and the derivative with respect to this extra parameter is called variation. So I will not fight against Lagrange nor Euler, and I will follow this notation. Just a side remark that the Lagrangian is not a scalar. Of course, if there is a privileged measure in the space of independent variable, then we may always split it into this volume element and the scalar. However, a priori it is not a scalar, it is a scalar density. Okay, calculus of variations begins with the following considerations, namely, we calculate the variation, which means just the derivative with respect to this epsilon. This epsilon stands here and there, so this is just the formula, which we rewrite this way. So we integrate by part. So this is an identity. It does not contain any specific information. Now, calculus of variation in its usual form consists, this part is called volume part, boundary part, because if we integrate, then indeed this is a boundary part, and calculus of variation begins in neglecting the boundary part. Namely, we assume that we are looking for a minimum, not within the space of all field configuration, but only those which fulfill some boundary conditions, which mean if phi is fixed at the boundary, it means that its variation vanishes, therefore the boundary. And of course, this way we obtain Euler-Lagrange equations, and it is an excellent strategy in logistics, economic, traffic engineering, and so on, whenever field equations are elliptic. And now I am going to show you that in hyperbolic field theories, this procedure is a nonsense. And to show this, let me consider two-dimensional wave equation, which is a mother of all dynamical theory. Yeah. This was already mentioned by Jerzy Kijowski that that Maxwell theory is practically two independent wave equations, not two-dimensional, of course, but also linear gravity can be reduced to two independent wave equations. Okay, so this is the mother of all dynamical theories. So the space-time is two-dimensional. The parameters are t and x. I always use dot for the time derivative and prime for the space derivative. So Euler-Lagrange equation is simply wave equation. And of course, we are able to solve this wave equation if we use the light coordinates. Using this light coordinates, wave operator is written in this form, so we see that the second order derivative with respect to both u and v cancel, and what remains is only mixed partial derivative. What does it mean? It means that whenever we choose a rectangle in this light coordinates, a rectangle, and we take a solution of wave equation and integrate it over this rectangle, this vanishes because this is precisely the wave operator. Yeah? But on the other hand, integrating the derivative is very easy because it gives boundary values. So after two such integration, we obtain this combination of the values of the function phi at corners. So I have proved that wave equation implies this identity for any rectangle in light coordinates. However, it is very easy to prove that also inverse is true. If a function fulfills this identity for any rectangle of that type, then it is a solution of wave equation. What does it mean? It means that if we want to impose boundary conditions in such a region U, then we must observe this equality, which simply means that the boundary value on the upper wall is uniquely given in terms of the value on remaining walls, which simply means that choosing boundary data at random, we have zero probability to capture any solution at all. This situation I would summarize as follows: that this strategy to derive field equations from the Lagrangian, consisting in neglecting boundary conditions or imposing boundary conditions, means that we are able to derive field equations under conditions that we already know. Because knowing how to impose boundary conditions, I have shown you, is equivalent to knowing, to being able to solve this equation. Therefore, it is a nonsense. For other, I will skip this. This is more complicated by Stillman algebra, but for a typical region in space-time, the problem of boundary conditions is a very interesting mathematical problem. I could give you one semester course on it. It is very interesting, but of course today I will skip it. However, the conclusion is that the set of boundary data which admit any solution of field equation is small. Typically, it is a singular non-closed subspace in the space of all boundary data. So better don't try to impose any space-time boundary conditions, because it is a very subtle problem, although it is still very interesting mathematically. Therefore, I go back when we write down this identity, because this is an identity, the strategy, which I call brachystochron strategy, consisting in neglecting the boundary part and trying to squeeze out the physical consequences using only the volume part, is a nonsense. I reject it, because imposing space-time boundary conditions is strictly forbidden. However, if you take Wheeler-Misner-Thorne book, which I consider is the best introduction to general relativity among all possible tests which I know, but as far as this problem is concerned, they of course follow this, this nonsense. And on page 220, they derive Einstein equations from Hilbert's Lagrangian, just calculating the volume, saying that there are still some boundary terms, but we neglect them. We even do not know, we do not try to calculate them because it is too complicated and it doesn't serve to anything. So I propose to replace this strategy, which I call, by another strategy, which I call on-shell strategy. which means that from the very beginning, I do not consider, because you see there are some derivatives, which means that I consider some jets of sections of some bundles, yeah? So my strategy consists in taking into account only those who annihilate the volume part. Therefore, you may say, which a priori fulfill field equation, but I still do not know those fields. I only say that on the shell are those jets for which the volume part vanishes. Okay. So, and therefore, if we take both parts, this is an identity. Whenever I annihilate one of this part, it is no longer an identity by an equation to fulfill. Therefore, I end up with this equation. And I will show you that this equation contains not only Euler-Lagrange equations, but also more. Therefore, it is useful because when I say that the previous strategy is a nonsense, I don't say that all those Euler-Lagrange equations which generations of physicists were writing down is nonsense. No, they are true. However, I will obtain them within a more general frame. Okay, so this is the fundamental physical equation. Whenever you decide, and this is an equation, it is useful to introduce those auxiliary parameters and rewrite this equation this way, or more precisely, this way. And this, what does it mean? This simply means that the Lagrangian, which depends on the field values and their derivative, its derivative with respect to the field derivatives is equal to those momenta, whereas its derivative with respect to the values of field is equal to the divergence of this momenta. So we see that first of all, this recovers our definition. It is no longer definition, but the field equation. And this is an additional field equation. And we see that when we plug this into that, we obtain the Euler-Lagrange equation. But observe that there is no integration. All this, when you try to minimize action, you have an infinite dimensional space of all those functions. And of course, immediately the question arises, which class, which topology, and so on and so on. But this is absolutely not important. Here, everything is finite dimensional. At every space-time point, we have a finite dimensional space of those parameters, and this is finite dimensional story. So we see that Euler-Lagrange equations, which are second-order equations for field configurations, are now replaced by first-order equations, but for two different objects, configurations and momenta. And it is, I believe, very important because in physics, momenta are not auxiliary objects. They are very important. Moreover, very often we do not know which part of field is more positions and which are momenta. We may exchange, and it is an important possibility. And this way, we have defined field theory in terms of a symplectic control theory. So, this is what I have written on a previous slide. If there is only one independent variable, then there is only one derivative, namely the one which I denote by a dot, and this equation can be understood better if we consider this not 2n-dimensional space consisting of q and pi, but 4n-dimensional space, this big space, and the dynamics is described in terms of a submanifold, which has half dimensionality. And this is just the definition. These Lagrange equations are just the definition of a two-dimensional subspace of this space, four-dimensional space. This observation was done by one of my teachers, already in the 60s, and I tried to generalize it. This mimics, in a sense, the situation in thermodynamics, where the thermodynamics of a simple thermodynamical body can be understood as a following theory. There is a four-dimensional space. These parameters are volume, entropy, pressure, and temperature, and the specific thermodynamical body is described by a two-dimensional submanifold described by this equation. Okay. So this equation is nice to interpret in terms of the control-response relations, which means that among all those four parameters, we choose two of them which we control, for example, V and S, and the remaining describe the response of the system to change of these control parameters. Now, the fundamental thing is that in all these cases, the big space carries, I call it P infinitesimal. It is a kind of a phase space, however, it is not a phase space which consists of P and Q, but also P dot and Q dot, carries the canonical, God-given, symplectic structure. In mechanics, it is just this structure. I tried to generalize it to field theory, and it was not very easy because there is something which was very misleading, namely that there is also another symplectic structure inside. And it turns out that I have found this generalization, and all this stuff had been published in our common book with Turchiev, that in field theory there is no symplectic structure inside because there are 4 times more momenta than positions. Sometimes people, nowadays, there is a new terminology, people call this object inside symplectic current, but it is not symplectic. However, this big space carries a regular symplectic structure, and that's all. Okay, so to summarize this symplectic control theory, so it consists of the following objects. First of all, there is a big symplectic space. This is in field theory, in mechanics, in thermodynamics. Then, physically admissible points form a submanifold, and this submanifold is Lagrangian. Lagrangian, which is isotropic maximal. Isotropic means that this symplectic space structure vanishes when restricted to this submanifold. And then all those formulae which I have written for you, for example, Lagrangian or Hamiltonian or anything else, consist in dividing coordinates in P into two groups, control and response parameters. For example, and this is described by a generating formula. This one in Lagrangian picture in field theory, this one in mechanics. Now, this, so the physics in this view is described as a control-response relation. However, the choice of control and response parameters is not unique. So, sometimes the choice is such that the control-response relation is a function, which means that it may be a graph of a mapping from control to response parameter. However, sometimes, very often in physics, we meet such a situation. Of course, if we insist in having physical laws as just function from control to parameter, then it is a disaster. Yeah? Because we have a constraint, some values of control parameters are excluded and control-response relation is multi-valued. But if we consider the dynamics as just a submanifold, then the difference between that and that, there is not especially big difference. This is vertical, this is not vertical, but they are just submanifold. Everything good. And conclusion is that regularity of the description, for example, Lagrangian or Hamiltonian, is not an intrinsic property of dynamics, but of the control model. Very often we deal with Lagrangian constraints, and when we pass to Hamiltonian picture, no constraints. And very often vice versa. No constraints on the... No. And now, why this picture is so important? Because because we may change the role of positions and momenta. Such a change can be called the Legendre transformation, and in thermodynamics, for example, there are many Legendre transformations which I was taught by Professor Verlean, because I had a very nice course in theoretical thermodynamics, which, according to Cara Theodori, is a nice differential geometry, okay? And this way, for instance, we pass from the internal energy to the enthalpy. In mechanics, this is also, we know how to pass from Lagrangian to Hamiltonian picture. We simply exchange the role of velocities and momenta as a control parameter. In Lagrangian picture, Q and Q dot are control parameters and P dot and P response parameters, and in Hamiltonian picture, P and Q. So yeah, so in field theory, there is a strange situation because there is a huge group of mathematicians who said that the field energy consists in replacing all the field derivatives with all the momenta. No, this is not the energy in the, which we physicists understand. To transition to the Hamiltonian picture, we know that the energy is not a scalar, but a component of the energy momentum. So to pass to Hamiltonian picture, we have to choose a reference frame, which means that we have to distinguish between time and space, and we treat in a different way space and time derivatives and space and time component of the momentum, and we treat this first, so we leave the space divergence, and this part we transform exactly as in mechanics, and this way, yeah, we obtain the field Hamiltonian, and which is a field energy density. Now I'm slowly coming to the end of my story. Gravity. Theory of gravity, a priori, it is a theory of two independent objects. A priori, they are completely independent, metric and connection. In the metric approach, metric is treated as a configuration while the momentum arises. And this is this formula which is written or derived on page 520 of Wheeler-Misner-Thorne, but there is also a boundary part. I am very proud because I have calculated this boundary part as soon as I read the Wheeler-Misner-Thorne. And this is very simple. In fact, maybe there is some momentum, which is a tensor with 4 indices. However, it is uniquely given by the tensor with 2 indices. And this tensor density with 2 indices is nothing but the contravariant density of matrix. In fact, it was already Vladimir Alexandrovich Fock who, in his book published in 1938, I believe, has noticed that for all those Hamiltonian considerations in general relativity, it is the formulae become much simpler if we represent metric not by covariant tensor, but by the contravariant density. And this is true. So now let me apply my online strategy, which means that I a priori neglect the volume part. So I see that metric arises as a momentum canonically conjugate to gamma, which is a field configuration. Now, when you read all those Einstein's trials to found correct formulation of general relativity, you immediately find that he was looking for an appropriate mathematical tool. Namely, he tried to understand what does it mean, the inertial frame. But the mathematics which was available at that moment was only Riemannian geometry, and the notion of the connection did not exist except for the Christoffel symbols. And this is why he ended up with the metric. But in fact, connection is a description of an inertial system, which means a class of coordinates such that the free-falling body satisfies this second Newton equation. But Newton was sufficiently intelligent that he noticed that when he wants to write down his second law, he must first define the first law, that there is an inertial system. But in Newton's time, everything was global because the universe was considered to be small. Now it is 20 orders of magnitude bigger than before. So I claim that general relativity consists in replacing the Newton first law by the Einstein's first law, which says that at each point locally, separately, there is a local inertial frame, which is nothing but the definition of the connection. Now, I wanted to tell you something about Palatini, so I will skip it, excuse me. And so finally, take seriously this observation. So if you take, if you assume that gravity is a theory of a connection, then these are field equations where P, we don't know what is some momentum canonically conjugate. So it is very easy to see that this equation may be easily rewritten in such a way that we upgrade this partial derivative to the level of covariant derivatives with respect to gamma itself, and these corrections transform the derivatives of gamma. By the way, these are derivatives of gamma. Whenever I add an extra term, these are partial derivatives. It is transformed into a curvature tensor. This is a curvature tensor which this is my private way to describe the curvature tensor. It is perfectly equivalent to the Riemann, but it is different and it makes the formula much simpler. If I use instead of Riemann, I use this curvature. So, but if Lagrangian is invariant, then it cannot depend separately upon gamma only via the curvature. Which simply means that the derivative of the Lagrangian with respect to gamma must vanish, so one of the universal field equation is this one, and the remaining equations mean that the momentum is the derivative of the Lagrangian with respect to the curvature. Now, the curvature, in a generic case, can be decomposed into three irreducible components. It is not an irreducible object, namely the Ricci, and Ricci again splits into symmetric and anti-symmetric part, and the remaining trace zero part. So we may perfectly say that the generic Lagrangian describing the theory of a connection may depend upon those three objects. The dual decomposition of momentum is again into three parts. Therefore, any theory of that type is split there, and it is natural to interpret the momentum canonically conjugate to the symmetric part of the Ricci as a metric. Okay? So now, of course, we do not know what is this L. So let us make, suppose that the God, when creating the world, has taken into account only this part. The God has told, let us choose such a Lagrangian which is not sensitive for those two parts. It is sensitive only for the symmetric part of the rigid tensor. Then the metric tensor is, of course, the derivative of the Lagrangian with respect to this. But there is only one way to manufacture the scalar density out of this tensor, namely the determinant. However, this formula is obviously wrong because it can be written only by a mathematician because the units are not consistent. Therefore, some constant is necessary, and we see that one of the field equations tells us simply that the connection is metric, which otherwise we assume a priori, but here we obtain it. And it is very easy to see that this is simply the Einstein theory with cosmological constant. The value of the cosmological constant is a function of this constant. That's all. Therefore, with such an assumption, we end up with general relativity, nothing more, nothing less. Now, if we assume that the Lagrangian may depend also upon F, we end up with electromagnetism, and it is very close to the old Weil proposal, who also tried to describe, to unify electromagnetism with gravitation. However, he was using very specific, because at that time people were thinking that the connection is nothing by the Christoffel symbols, so Weil only generalized it a little bit. But here it is really an electromagnetism. However, for very weak fields we obtain just Maxwell theory, but for strong fields this is no longer linear. It is a kind of a Born-Infeld electrodynamics. And what about you? So, I would say that it could be a very good proposal to try to describe dark matter with you, but of course this is not correct, because the very invention of dark matter is a proposal to describe something new with terminology taken from the old theory. No, but I strongly believe that this U is another field which may somehow help us to understand this, how the gravity behaves on the large scale. Large, I mean the universe scale. And this is the end of my story. I strongly believe that this U is practically constant within our, lambdas are very big, therefore for our practical purposes it is constant, and it does not change very quickly. Therefore, for our gravitodynamics, it is useful to consider this as a constant in our tiny place of the universe. Thank you very much.
Thank you very much for the very much condensed lecture. Questions? There are many ideas, so people have to digested.
Yeah, I think so.
Okay, so thank you very much again.